Welcome back to Step Up Med's Cardiovascular Physiology series. In this episode, we break down how your body monitors and regulates blood pressure, both in the short term and the long term. We'll explore baroreceptors, chemoreceptors, the RAAS system, and the kidneys, all working together to keep your pressure stable. Let's get started. By the end of this episode, students should be able to define systolic, diastolic, mean arterial pressure, MAP, and pulse pressure. Understand short-term and long-term mechanisms of BP regulation. Describe the role of baroreceptors, chemoreceptors, and the RAAS system. Apply concepts to clinical conditions like shock, hypertension, and blood loss.
Blood pressure is the force of blood against arterial walls. We focus on three key values: systolic pressure, peak pressure during ventricular contraction; diastolic pressure, lowest pressure during relaxation; pulse pressure, the difference between systolic and diastolic. Mean arterial pressure, or MAP, represents average pressure in the arteries and is calculated as MAP approximately equals diastolic plus 1/3 of pulse pressure. Clinically, MAP must be maintained above 60 mm of mercury to ensure perfusion to vital organs. And remember, MAP equals cardiac output times total peripheral resistance. Baroreceptors are stretch-sensitive nerve endings located in the carotid sinus and aortic arch. They respond rapidly to changes in blood pressure. Increased BP means more stretch, which causes increased baroreceptor firing. This activates the parasympathetic system, reduces sympathetic tone. This decreases heart rate, contractility, and vasoconstriction. Hence, BP decreases. Decreased BP leads to less stretch and decreased firing. As a result, the sympathetic system kicks in. This increases heart rate, vasoconstriction, and cardiac output. Hence, BP increases. This is a fast, moment-to-moment regulator, especially important during posture changes. But with chronic hypertension, baroreceptors reset, making them less effective.
Chemoreceptors, located near baroreceptors, detect changes in oxygen, carbon dioxide, and pH. Low oxygen, high CO2, or low pH right-pointing arrow triggers sympathetic activation, right-pointing arrow vasoconstriction, and increased ventilation. The CNS ischemic response kicks in when brain perfusion drops severely. It causes intense sympathetic output as a last-ditch effort to raise blood pressure. This activates when MAP falls below 50 mm of mercury, usually in severe shock or blood loss. For long-term control, your body turns to the RAAS system. A drop in renal perfusion or low sodium levels triggers the juxtaglomerular cells of the kidney to release renin. Renin converts angiotensinogen from the liver into angiotensin I-ACE, mainly in the lungs, converts angiotensin I into angiotensin II. Angiotensin II causes vasoconstriction, right-pointing arrow increases TPR, stimulates aldosterone, right-pointing arrow promotes sodium and water retention, stimulates ADH release, and thirst right-pointing arrow increases blood volume. All of this leads to a gradual increase.
The kidneys are the ultimate long-term regulators of blood pressure. They adjust plasma volume via sodium and water excretion. If pressure is high, they excrete more fluid. If pressure is low, they retain more fluid. Additionally, the heart itself helps by releasing natriuretic peptides like ANP and BNP, triggered by atrial or ventricular stretch. Cause vasodilation, promote natriuresis, sodium excretion, inhibit renin and aldosterone release. Net effect, lower blood volume and pressure. Let's apply this. In hemorrhage, baroreceptors rapidly activate sympathetic tone, while the RAAS system kicks in over hours. In shock, CNS ischemic response takes over. In chronic hypertension, baroreceptors reset and the RAAS system may become overactive. Pharmacology tie-in: beta blockers reduce renin release. ACE inhibitors and ARBs block the RAAS pathway. Diuretics reduce blood volume. Nitrates reduce preload and afterload. Let's summarize. Blood pressure equals cardiac output times total peripheral resistance. Short-term control, baroreceptors and chemoreceptors. Long-term control, RAAS system, ADH, and the kidneys. Natriuretic peptides oppose the RAAS. Clinical states like shock, blood loss, and hypertension challenge these systems.
Now test your knowledge with this quick exam-style question. Which of the following best describes the function of baroreceptors? A. Measure blood oxygen. B. Measure blood pressure via stretch. C. Control kidney perfusion. D. Stimulate ADH release. Leave your answers in the comments below. Thanks for watching episode 11 of the Cardiovascular Physiology series. Up next, we'll explore shock physiology, What happens when perfusion fails? Don't forget to like, comment, and subscribe to keep learning with us.